So back to the Western Scheldt. The question basically is, like, can we predict what's going on here? And as a scientist, you start then by simplifying things, because you want to understand things step by step. A definition of a good model is that it should be complex enough to explain reality, but it should be simple enough to understand what's going on. So at that ballpoint you want, at that sweet spot you want to operate. And so the first thing we did was setting up a model like this, which is about 80 kilometers long, which is the length of the Western Scheldt, roughly. There's no river flow, because the river flow in the Western Scheldt is very limited. There's no sediment supply, it's all a sandy system. And this is where the tidal motion is forced, the LTV. And then the grid size is about 100 by 200 meters. So we are covering basically the model in high resolution.
But the river is meandering, this is straight.
Sorry, there?
The river is meandering.
Yeah, but we want to do things as simple as possible. So first we want to explain or understand, if we have a very simple system like this, with an academic system, I would say, then because then we do things step by step. The next logical step indeed would be to make a shape. And but this is happening. And this is a run I did about 15 years ago for my PhD, and that was a run that was running also for a month on a PC. And it is a run covering about 3,000 years. So under 3,000 years of constant forcing, you see that this is happening. So in the beginning, you see a lot of morphodynamic development. There's a lot of activities. And later on, you see that the morphodynamic activities decreases. And it becomes more stable. There's a kind of trend towards equilibrium. But it takes a very long time. It's not something that happens in an overnight or so. It's taking hundreds of years.
Is this the effect of the river and the tidal effect, or the tidal only?
Tidal. So basically what this model does is, for 1,000 years, doing a tide back and forth. And then in interaction with the sediment, it shapes this morphology. You see a nice alternating bar pattern now there. That's also happening in tides. You see it in rivers too, but also here.
But just to make it simple, you did not consider the flow coming from the river?
Right.
And the groundwater also?
Right.
Does not have
No,
any?
nothing.
But usually that 3D does, takes into account the...
It can.
It can,
if you want, yeah.
Okay.
Yeah.
But how I'm going to simulate something like this if I didn't at least take like the flow from the river? Like this is the natural state that I have flow in the river and I have tidal.
Well, the flow in the river is about 500 cubic meters per second maximum. If the tidal cycle, say it's like this, and let's say that this is 1.5 meter, the amplitude is 1.5 meter. The length is 80 kilometers, the width is 2.5, so you may argue that a volume of 1.5 times 80 times 2.5, so that is 120, 240 is 300, well, 10 to the power 3 cubic meter per 6 hours is entering the basin, and it's leaving the basin the next 6 hours. So how much is that per second? Can you calculate that? 300,000 divided by 3,600. 300,000 divided by 3,600. How much is that?
It's cubic meter per 6 hours.
Yeah.
Makes sense.
800. Almost.
Yeah, 3,600 because it's hours from hours to seconds. So this number divided by 3,600 times 6.
830.
830 cubic meter. Somewhere I must make a mistake there. This is also 2.5, 10.3, so this is 10.6. So this is 830,000 cubic meter per second. Am I right?
What?
If it's power 6,
Yeah. Yeah. So this is the discharge, the tidal discharge through this cross section. Like this and like that. So back and forth. And that's not, I mean, and the river discharge is 500 cubic meters per second. So that is much smaller than the tidal discharge. And also, if you go to the Yangtze, for example, the Yangtze River, the maximum discharge there is about, how much is it? 80,000 maybe? 80,000 cubic meters per second. It's still nothing compared to what's happening here in Holland, in the tide. And so the tidal power is much larger than the gravitational power. And it's going back and forth, so it's not only in one direction, it's two directions, and that makes life a little bit more complicated. But if you want to really understand what's going on, you start studying coastal engineering next year at IHE. That's possible. Anyway, we are going back to this movie. It's finished now, after 4,000 years. And you see the last 1,000 years, not much happened anymore.
Yeah, but can you extract tables with values from the values?
Yeah.
Only such graphs.
So the nice thing about Delft 3D is that you have a virtual laboratory. So as a matter of fact, you can put measurement equipment virtually. You can, if you want to, at this point, if you want to know every second what is the velocity, what is the water level, what's the sediment transport, you can have that.
Okay.
Yeah. But a movie like this, if you have that for every point, it would generate terabytes of data, and that's maybe not very useful.
Yeah, because I was wondering, like starting maybe now or maybe some few years later, like we're not able to see it properly, that there's changes.
Right.
So I was wondering whether we can see them in tables
Or read a paper, because I wrote that thing down.
Yeah.
But you see indeed after 1,000 years everything seems to be in equilibrium. And if you look very carefully, you see here still the migration of the banks seaward. So what is Delft 3D doing? I think Professor Rolfing yesterday explained that to you a little bit. That is the mass balance equation and the two momentum balance equations in x and y direction. Where this is saying if the water level changes, there must be also a change in velocity. If it goes, the water level goes up, there must be water level coming into that cell. And this is then the inertia, time derivative, the advection. This is the advection terms, the pressure terms, water level, friction, and viscosity. And this is then Coriolis force for the larger systems. And this system basically has three unknown parameters: water level and velocity v and velocity u. It's and also 3 equations, so you can solve the problem, and you know the velocity and the water level at every point in your grid. If you know that, you can calculate, for example, by a sediment transport formulation, you can calculate sediment transport. And if you know the gradients of the sediment transport in space, every time step, yeah, if you have a cell and sediment is going out, you know that there's erosion, and if there's sediment coming in, there's deposition. Yeah, you can calculate bed level. So how does that work? You have your initial water bed level, you calculate your hydrodynamics, your sediment transport, your bed level update, and then you apply a morphological factor. What is a morphological factor? Maybe you can explain.
I think it's if we have a time step every 1 second in hydrodynamics, we can multiply it by a factor to get to make the morphological
Right.
updated every 10 seconds. Depend on the factor we have multiplied the hydrodynamic time step by this factor.
Yeah, yeah. And why would you do that? Huh? Because if you have 10 meters of water and your model calculates a bed level change of 1 millimeter, it's nothing. And we want to speed up things a little bit. So what we are doing, we'll multiply the bed level change with the morphological factor. So it is then not 1 millimeter, but let's say 10 centimeters. If you apply a morphological factor of 100. So a bed level change of 10 centimeters is still nothing compared to a water depth of 10 meters. So probably that bed level change will not affect the hydrodynamics in that cell at that moment too much. That's the assumption that you're going to make. And the advantage is then that your bed level changes, your modeling is much more fast. On the other hand, if you take your morphological factor too large and your bed level change is 2 meters with the morphological factor and your water depth is 3 meters, then of course it's too much. Because that affects how the water moves in that cell. So we don't know how much the morphological, what the value should be of that factor. But typically 100, 200 is safe. If you have waves, it's 50, 200. In these type of runs that I showed you, you may even go to 400, 500, 1,000 maybe. So that is all possible. 2 important effects for morphological people. That's the lateral bed slope effect. You can imagine that if this is a cell, but that cell, the bed level of that cell is inclined. So it is not flat, it is tilted. And that means if you calculate your sediment transport in that direction, because it's the direction of your flow velocity, something else happens with that sediment, because it falls down the hill. It falls downhill. And that is this effect. So Del 3 takes that into account. It's basically a correction factor for the inclination of the bed level in your cell in downhill direction. And that is called a bed slope effect alpha Bn. That's in your morphol. And similarly, you also have that if the inclination is in the direction of the water flow. So this used to be when the inclination is perpendicular to the water level direction, to the water velocity direction, and this is when it's aligned with the water flow. And this is called alpha Bs. Well, these are important calibration parameters in your run. The next step in our quest for the Western Scheldt modeling is to make erodible banks. So you then can imagine that you have a dry cell and a wet cell. And at a certain time step, you see the erosion of the wet cell. That can happen because of the gradients of the sediment transport. And when that wet cell is adjacent to a dry cell, we assign the erosion of that wet cell, not in the wet cell, but we assign it to the dry cell. And that means that basically sediment is transported from the dry cell into the wet cell. So you get this result. Then this cell becomes wet, and if this cell erodes, it takes it from this cell, and so on and so on. So, is this true? I don't know. But it is a way for Delft 3D to deal with bank erosion mechanisms. Other procedures are with cut cell approaches and with polygons, and that's currently under development, but I'm not touching that right now. So this is also a parameter that you can adjust in the more file, that you can play with during your exercises. And maybe you did that already. So this then shows a movie. When I find my mouse. Of a similar basin, but now the length is 300 instead of 80. And you see here the erosion of the banks. And you see that the sediment is supplied from the banks into the basin, and then the basin exports it towards the delta, actually. So my profession is estuaries. And some other people's profession is deltas. And I know for sure that you can earn much more money with deltas modeling, because that is for oil companies it's very important. Because if you have a delta, that's also often an environment where you can find oil and gas. And estuaries is not so interesting. Anyway, 5,000 years, and you can still see that there is a lot of morphodynamic development. Well, why is that? Why is the fixed banks stable after 3,000 years, and why is this one continuing?
It's erodible, so it will be affected always with the flow and be eroded.
Yeah, it's erodible, and because it's erodible, there's so much sediment supplied into the system, and it wants to get rid of it, and it's a process that continues and continues. Whereas in the other basin there was no supply of extra sediment, so then it was much more easier to go to that equilibrium. And you also see that in the width average longitudinal profile. This is then for the fixed banks, and this is for the erodible banks. And this one you see that it slowly goes down, erodes, by transporting sediment. And here you can see that it first goes here, and then it erodes. So you see the same trend, but because of the extra supply of sediment by the eroding banks, it first fills up and then it indeed exports again. Well, you can do all kinds of analysis right now with the water levels and the velocities and so on. This is the ebb and flood velocities, for example, and here you can see that this is the initial, that is the stars, this is the flood flow, this is the ebb flow, but it's the same for both basins. And then after 200 years you can see that the velocities, they increase a little bit because of the pattern formation. You have you can see that the channels are incising and the shoals are developing, and that means that the velocities are increasing a little bit. But later on, that's the squares and the triangles, you see that the velocities, they decrease because the channels get deeper and the shoals get higher, and basically it evolves into a kind of configuration, the morphology evolves into a kind of configuration where it feels at ease and there's less morphodynamic activity. And less morphodynamic activity means lower velocities. And you see the same trends for the erodible banks basin. So what timescales do we see in this movie? We first see the timescale of the basically I can see two timescales. One is the pattern formation, the first decades, I would say, where you see very quickly that They define here's a channel, there's a shoal. And then later on you see that continuous export of sediment. So once this alternating bar pattern has established, it is basically in equilibrium, but then you see this very slow migration of these bar patterns, and that's what I basically consider to be the two time scales that are in this picture. One to the pattern formation, channel shoal systems, and the other is to the width average profile, so it's basically the time scale of the entire system. So what is the basin aiming for? It's not chaos that continues forever. No, why does it go to a kind of equilibrium? And there's all kinds of concepts, and this is an interesting concept by Rodriguez Actor, and he says like, well, consider then the energy dissipation formulation. And what is energy dissipation? That's a function of shear stress and sediment transport. So the more shear stress you have, the more friction there is, and more sediment transport. Also, it costs energy for the basin. And what he says, like, well, it's a lazy system. So it wants to work, it needs to work, like people. But it's a lazy system because it develops towards a state of less and less energy dissipation. So it organizes itself in such a way that it dissipates less energy. And again, we know at every point, at every time, we know the energy dissipation. We can calculate it. Basically, we can calculate the friction or the sediment transport if we do that. That's basically what we do. And if we plot that, you see that this is happening. So this is in the beginning, the energy dissipation levels during flood and during ebb. And this is the development over time. And here you can see that the system in the beginning has a lot of energy dissipation, a lot of sediment transport, it's shallow, a lot of morphodynamic activity, and later on it decreases, and the activity during ebb and flood becomes equal, and it feels at ease. It's like it made its own bed, and it starts to sleep, basically.
I have a question.
Yeah.
We're not considering the dissipation of the waves?
Waves are not included here.
Okay.
Only tidal wave. It's a tidal wave.
Okay.
So you're right, if you look at an estuary, you see all. So this is only tidal movement and sediment. And if you look at the real estuary, you see wind waves, you see vegetation, you see storms, you see mud, you see sand of different fractions. You see much more complexity, but that's what we will add. First we want to understand the simple system.
So there's no dissipation of tidal waves?
There is.
But we don't consider that.
The dissipation of the tidal wave, it is included actually. So if a tide enters this basin, it loses its energy because of friction.
Yes.
And that is included in the formulations over here. So these are basically, this is calculating the dissipation level at every cell.
Okay.
It's a good question. Because I'm not explaining you the full thing over here. If you really want to have the answer, that is very advanced. That's this one, and I didn't discuss that. So in the beginning you see this is the tidal amplitude. And when the tide enters the basin, it loses its energy. That's normal, you can see that also in rivers. Because it's shallow. But the strange thing now, it exports the sediment, it becomes deeper, and with that the tidal amplitude increases. So what's happening here? The tidal amplitude increases in a deeper basin, and that's true because we measure it.
Okay.
So the farther you go inland, the higher the tidal difference becomes. Why is that? Because if you take a tidal wave, this is the length of the tidal wave, and I have to continue here. But this basin length is 80 kilometers, and it is on 1/4, a quarter of the tidal wavelength. And that means it becomes a resonant basin, like you have resonance. And that is happening because if it becomes deeper, you get rid of the friction. If you get rid of the friction, you get the resonant behavior becomes dominant.
This is why the amplitude.
And the resonant behavior is because and that's the results in the tidal amplification. Yeah, so that's the entire story. But your question was on energy dissipation levels. Huh? And you can calculate by definition what energy dissipation is. That is a velocity to the power 3. That's the energy dissipation, and you can translate it then into this figure for the fixed banks and this figure for the erodible banks. And now you can see a hump over here, and that hump is caused by the supply of sediment from the banks. That makes the basin shallower, and that means that there is more morphodynamic activity, but on the longer term, indeed, you see the same decreasing trend. Well, you can look at here, and the question is how. If you remember my lecture from the beginning, we talked about this empirical relationship, and the relationship between the tidal prism and the cross section, and we can say like, hey, how do the model results, how do you compare to that? And it seems that the model results quite nicely fit that empirical relationship. So this is the first step, like, is there, it's nice that we see the system right now, it's very academic, it doesn't exist in reality. And how real is this system? And this is then the first step that we say, like, hey, if we compare it to empirical relationships, it seems to do a pretty good job. So concluding remark, leads to equilibrium on the short time scale. On the longer time scale, you see there's no equilibrium, but there is a kind of asymptotic behavior towards equilibrium. And there's indicators for equilibrium also because it fits the empirical relationship, equal ebb flow duration, more uniform distribution of velocity and energy dissipation along the basin, and decreasing energy dissipation rates over time. It also suggests that the estuaries that we see are not in equilibrium properly, because this is a 3,000-year calculation for an 80-kilometer basin, and it takes a very long time to reach that state of stableness. And in reality, you probably have sea level rise over the past 3,000 years. So, as a matter of fact, many of these systems are still adapting to that Holocene sea level rise. Well, that's my question here. But I'm not going to deal with that.
Yesterday we were asking the question, Gamal asked the question, and we were hoping that today we'll see it more about whether we will reach this equilibrium or not. Because, like now you were mentioning the adaptation with the Holocene climate, which is actually changing also.
Right.
So, and with the human interventions and so on, I think it will never be reached.
If you look at the system, if you look at the system right now, you measure the bathymetry. What are you measuring? Well, basically you measure the remnants of past developments over thousands of years and of anthropogenic interferences with sediment supply and land reclamations and stuff. And they all have a kind of inertia in the system. So for every step you take in that basin, it needs some time, there's an adaptation time scale related to that. And the things that you see over there is the kind of summation of that. and most of them, they are still continuing. Yeah, but it is asymptotically. I think it's a very important notice that in principle this system wants to go to a state of stableness. That's a very important note. And whether or not that stability is reached maybe is of second order at this moment. But at least we know what kind of system we're dealing with. So, indeed, this is all very academic, so let's make life a little bit more complicated. Because we dealt with the bathymetry and the hydrodynamics, the interaction, and now we're adding the geometries of the plan form. And this is then the Western Scheldt. You can see that the shoals are allocated somewhere and not somewhere else. And why are they allocated over there? And we made a model for that. We thought like, hey, let's start with a flat bed and let Delft3D generate then the morphology, and let's look at if it generates a stable morphology, what it will probably. How does it look like? Oh, I forgot the recording. How does it look like are the locations of the channels and shoal the same as in reality? And that is this movie, basically. So a flat bathymetry. You can see indeed the same development as the earlier movie, where in the beginning you see a lot of morphodynamic activity, and later on there's less morphodynamic activity. And this is a run that covers about 200 years. And well, the question is, how does it look like? This is the 1998 bathymetry, and this is the development over time. And the question is like, how much does this look like this? It's good to know about the parameters that we added here. It's only tidal forcing, simple transport formulation, bed slope parameter, 2D, 3D, so I did all kind of sensitivity analysis here to look at what processes are important, which ones are not. And this is then the outcome. And on the upper panel you see the measured profiles, and here you can see the model profile. So is this good or bad? And this is with Engelund Hansen, 3D, and ODM2. Is this good or bad? And you see these nice similarities here. And here as well, but this is much deeper here. There's also differences, similarities and differences. And this may be the best one. Because here we included not only the plan form, but there are layers in the bed that are Pleistocene, and they're very difficult. It's clay, stiff clay. It's difficult to erode that. We know where these layers are, so if we put them in the model as well, we get this, and this is basically the best run. It's not performing well here, but here it performs, well, almost exceptionally, very good actually. So basically this suggests that the shape of the basin determines where your channels and shoals are allocated. Because of time, I want to conclude here a little bit, because I think it's time for you to start modeling yourself. So the conclusions here, so the model reproduces nice and realistic patterns, and major tidal forcing determines the patterns. We don't need storms, we don't need different sediment fractions, we don't need sedimentation, we don't need 3D. No, it's really a very simple model that we're performing here. And one more question. Can I do one more step? Because then I finish my Western Scheldt case study. This is the weather forecast. So with this weather forecast, we predict the temperature with models, and or the rain or whatever. And this is basically also the trend. of our forecast value with different scenarios. You see in the beginning the models, they correspond quite well, and later on it becomes a chaos. And it becomes the weather system itself is a chaotic system to a large extent, at least in Holland. It's very difficult to predict our temperatures or rain. And the question now is that also true for our morphodynamic models? Because there's so much non-linearity in our models. Already in the equations, the advection part or the friction part is non-linear. It's due to the power 2. And the sediment transport is due to the power 5 maybe, or very non-linear. How does a system like that behave over time if you start modeling that? So let's assume that this is time, and this is morphodynamic activity, or cumulative morphodynamic activity. In the beginning there's a lot, and later on it drops a little bit. And if we, at a certain moment now, if we go to the Western Scheldt and we start modeling, we take that time point. And what is our model doing? Which one of the lines do you think?
Blue.
So, sorry?
The blue line, maybe.
You think it's the blue line?
Yeah.
Who
I
says
think it's
it's?
overestimated.
It could be any one of the four.
It could be any one of the four, yeah. Depending on,
The problem?
Uncertainty.
yeah, it depends on uncertainty. Uncertainty of what?
Of weather, of anything, of the tidal. Like
And the
profile.
data.
Well, the tide is very predictable. I mean,
Yeah,
But
but
the
the
climate
measurement.
change is not predictable.
the-
The climate change is not predictable.
No, that's right. So it also it relates to the time frame here. Is that 1,000 years? Is that 1 day? That's true. Let's say it's 10 years. Let's say it's 10 years. Basically, the question is: can we predict our morphology? Because these academic case studies I showed you before, it's all quite academic. It's not like real life. Actually, reality is much more complicated. And can we believe that actually? That's a question. Well, take a color in your mind. We're going to the Western Scheldt with a model called Finel 2D. It's basically Delft 3D. Does the same things on a triangular grid, very high resolution. So it resolves basically the major morphodynamic patterns over here. And I'm going to play a little game with you. Over the past 110 years, we have had bathymetries from 1860 to 1970. Also later, but in 1970, the major dredging operations started. So that's why we do it in a pristine system, basically. So every 30 years. And I'm going to show you the results of our model and the measurements. So this is the erosion and sedimentation patterns. Red is deposition, blue is erosion of the measurements and of the model. So and this is after 18 years. So is this good or is this bad? That's the first question.
There is some overestimation and some
For me, it's good. Like,
underestimation.
Yeah, you like it.
In some places, I think it's good. In other places, I think
Yeah.
a lot of difference.
So okay, keep that in mind. Now, the next question is it improving or is it worsening over time? Yeah, so I'm going to show you a sequence of slides. 1, 30 years, 45 years, 71, 95, 100, 110.
I think it's the same trend.
it's improving.
Who says it's the same? I'm going back again. 18, 30, 45, 71, 95, 100. 10.
Improving.
It's improving.
It's improving. Yeah, it's improving. So we developed a model that the longer you run it, the better it becomes. That's a good model. Huh? This is astonishing, huh? It's very counterintuitive. Because you would expect with a model like this, with the weather forecast, that it would expand. I mean, but it converges actually. So the longer you run your model, the better it becomes.
But this is like pure chance or what?
Well, I'm asking you.
Because it's based on data that are not also very accurate. Or it's prediction.
I think it's in the beginning the changes in the morphodynamics is rough.
Yes.
Because of the erotic process, but after with time it's settled, so it can be predicted more accurately.
Yes, I think that's part of the explanation. The model is wrong. It makes a mistake. It's always different. Huh? There's a difference. Because we don't have waves, we don't have storms, we don't have short-term effects, we don't have gradations in sediment supply, we have constant turbulence model.
But I think this all these factors compared to, for example, the discharge of the tidal is like secondary factors. So in the model is taking the major factor or the dominant factor, which is tidal discharge,
Yeah,
and the difference come from this small factor.
yeah, I think so. Two effects. You have the error and the signal. And I would say that the error is always there, and maybe it increases over time. But the signal is also there. The signal is the truth. Huh? So there is some. In the beginning, the secondary effects are larger than the primary effects, but then later on, the primary effects become larger than the secondary effects. I will show you later. But first, I go back to the assessment of a model. So we took a visual at the thing. Eh? So we said like, it looks like it is a good or bad. We want to put that in a number. And this is called the Braille-Scale score. And let's see if we have a beach over here. And after a storm, this is the beach. So there's a clear signal in it. There's erosion here, there's deposition over here. Now, what can a model do? That's the why. It can predict the same signal but with a different amplitude. That's the dashed line here, with a lower amplitude or a larger amplitude. It can predict the same signal with a good amplitude but shifted with a phase, not at the same location as I would call it. And it can also make the error that the average value is different, that the location and the amplitude are the same, so the phasing and the amplitude are the same, but basically the mean value is different. So there's basically three errors that a model can make. So amplitude, phasing, and bias. And they all have an effect on the Braille-Scale score. So 1 is perfect, and 0 is bad. If we keep that in mind, there we go again. This is the Braille-Scale score. It's 1 minus the error divided by the signal, where this error is the difference between model and measurements. And signal is basically what the measurements tell you. And that is basically the signal. And if it's below 0, the error becomes larger than the signal, and that basically implies that your model is worse than, is doing a very bad job, and you should not have, your initial bathymetry is better than your model outcome. So you should not have started your model. And this is the Braille-Scale score over time of this model. And in the beginning, it is negative. It is negative. So people say from 18 years onwards, it's not a very good result. I agree. Some things look like it. But you see also the increasing and improving trend over time. And that is remarkable. Now, because the Braille skill score is the error divided by the signal, you can also calculate that. And you can say, well, this is the error, and this is the signal. And why does the Braille skill score now become larger than 1? It becomes larger than 1 because the signal becomes larger than the error. In the beginning, that's not true. That's what you told me already. The error, the secondary effects are larger, but later on the signal kicks in and it becomes better. And it's not true that the cumulative error becomes less over time. There's always an increasing trend, so the error becomes larger and larger over time. So the model performs worse and worse in that sense. But in large parts of the domain, there's also an increasing trend in that the model can reproduce the signal. It captures basically the development, and that is the cumulative effect of the tide interaction with the shape of the basin. The morphodynamic developments can only go in one direction, because that is how the shape interacts with the tide. And that's a cumulative effect that in the end becomes dominant. So 30 years ago we could model only 10 years, and then we were here. And then we said, well, let's stop the modeling because it's bad. But once you continue on the supercomputers, you see basically this result. And you say maybe it's a coincidence, but we started at different moments in time. So this is 1860, 1970. This is 31 to 70, the red one, and the blue one is 1965 to 2002. And you see that they all, the dashed line is then the signal, and the solid line is the error. That it doesn't matter. It's always after 30 years, the signal becomes larger than the error. So the 30 years is a kind of morphodynamic spin-off time. There's two explanations for that. One is we don't take into account sediment grading, wind waves, storms, maybe neap spring tidal cycle. And that's why the model makes an error. And of course also the model is wrong, because it has a turbulence model that we cannot validate. Maybe this is 2D, it's basically it's 3D, we have salt freshwater mixing, it's all not included. So in the beginning the model adapts the bathymetry to its ill-defined conditions, but later on in a cumulative way it also captures the real development. So if we go back to our, I think the blue line, or maybe the orange line would be the right thing over here. And this is my final slide. How true is then our modeling exercise of the fixed Banks basin, where we saw the decreasing energy dissipation levels? Well, we can now compare that to our model of the Western Scheldt, and also in our Western Scheldt model we see the decreasing energy dissipation levels. So something that we predicted by our model, we also see in reality, and that systems like this, they tend towards a state of less and less morphodynamic activity under relatively constant forcing conditions.
So if I have data for like 30 years for the river I'm working on,
Yeah.
I will be kind of sure that the result will not be good enough.
Well, it's also a case-by-case thing.
Okay.
So usually the morphodynamic development in tidal conditions is slower than river conditions, because river is in one direction, tide is back and forth.
Okay.
So typically the morphodynamic adaptation timescales are an order of magnitude smaller in tidal systems than in river systems. So 30 years maybe quite nice. Well, look, if your forcing conditions are relatively simple, you can also model them. And so the simpler your forcing is by a hydrograph that is always there, the sediment that is relatively stable, then it also becomes, then your morphodynamic spin-up time would be maybe 10 years. So the morphodynamic spin-up time would depend on the system. For river systems, it would be typically smaller than for tidal systems.
Okay, and if I increase the morphological factor, will it give better results?
Well, it gives the results faster. If it's better, you have to do by trial and error. Because, but typically, what I see is that morphological factors up to 200, they're safe to go. And if you start increasing morphological factor, not so much is happening, but the system becomes more diffuse. So in reality, you would have, I think that a bar that develops like this. Then with a high morphological factor, you would see a more diffuse system. So you can still see the bar migrating, but it becomes more numerically diffuse actually. So well, you have to experiment. So concluding remarks. I think this model then performs well in confined systems, where basically the shape of the basin determines where the shoals and the channels are. It's first in the first decades, but increases over time. Longer term predictions seem more valuable than shorter decadal predictions. But this is for a system. If you want to study the impact of a groin construction in your river, it's a big signal. And there the model will perform better, I would say. Yeah. Because it's a strong interference with the system as such. The question is how to decrease the morphodynamic spin-up time and, for example, sentiment dynamics. So coming back to this shoal, because that was the start of my lecture. If you really want to know more about what's happening with the shoal and the sea level rise scenarios, you should take a look at this publication that just came out by Yiqing Zheng that worked on this with a model, with waves, with mud, with sand. So it's a very complex model, and that describes basically the fate of the shoal. I'll leave that to you to study yourself. So this is it. I talked enough. I'm going to grab a coffee, and after the break we can continue with the exercises. Exercises are all online, so just plug in your ear things and just do it. If there are not more questions.
The 6 parts?
But I have a question. What is the signal again? The signal and the error? I didn't get that.
Yeah, what is the signal? So the signal is basically, the error is the difference, sorry. The error is the difference between model and measurements. The signal is the measurements.